A simple graph is one in which any two vertices are directly... Oh, we always get this, definitely. I'm not going to read this out. We know this. And the thing about connected graphs as well, and simply connected, a fairly standard thing that we always get. Molly says that she's drawn a graph with exactly 5 vertices, having vertex orders 1, 2, 3, 4, and 5. State how you know that Molly is wrong. Well,
because Molly's a twit.
leave Molly alone. It's on the video. People watching this might actually be called Molly. How do we know that Molly is wrong? Well, actually, a few people answered this in terms of the whole simple and connected stuff. But it's not about that, is it? Because the question doesn't say she's drawn a simply connected graph. It just says she's drawn a graph. So it's not about any of this simple or connected stuff. It's just going to be a more basic thing than that. And one of the basic things we know about graphs is that the order, if you add together the orders, it must be an even number. Because every edge in a graph contributes 2 to the total of the orders, because it's got 2 ends to it. So the sum of the orders must be even. 1 plus 2 plus 3 plus 4 plus 5 is not even. So the answer to part 1 is that the sum of the orders is odd. And it can't be, a graph must have the sum of all the vertex orders must be even. So it can't have an odd number of odd vertices. We've got to explain something about how that doesn't work. It's not possible to do that. Part 2 says Holly now has drawn a connected graph with exactly 6 vertices, having vertex orders 2, 2, 2, 2, 2, 4, and 6. Explain how you know that Holly's graph is not simply connected. Okay. First thing to note for this, which of the vertices is the problem in this? It's the one with order 6. Because if there are only 6 vertices, and one has order of 6, then it must either connect to itself, or it must connect twice to another of the vertices. Therefore, the graph isn't simply connected. And that's what we've got to explain. The vertex of order 6 that's the problem. Explain it however you want. It must either join to itself or twice to one another. It has to be, there's only 5 other vertices for it to join to. So therefore, if either of those two things are the case, therefore it's not simple. Because we'd have a duplicate or a loop, and that stops it being simple. Part B, determine whether Holly's graph is Eulerian, semi-Eulerian, or neither, explaining how you know which of these it is. To be Eulerian, a graph doesn't need to be simply connected. It just needs to be connected, and it needs to have all the vertices of even order. So, part B, the graph is Eulerian. All the vertices are even. Okay. And notice it did say it's a connected graph there, so that's the other bit. I actually wrote in my answer, I wrote and it's connected. But they didn't require you to say that in the exam. Part 3 of this, Ollie. We've now got Ollie involved. Ollie, we've got Ollie in our class as well. Internet world. Ollie has drawn a simply connected graph with exactly 6 vertices. Should I not have introduced Ollie to the world? He's keeping very quiet. Yeah, okay. State the number of possible values. State the minimum possible value of the sum of the vertex orders in Ollie's graph. Okay, it is a simply connected graph. It has exactly 6 vertices. If you draw a tree that connects 6 vertices, then you can connect all 6 vertices together with 5 arcs. That's the minimum number of arcs, isn't it? So 6 vertices, what are we on? Part 3a. 6 vertices must have at least 5 arcs. To be connected. If we've got at least 5 arcs, a minimum of 5 arcs, each arc contributes 2 to the total of the orders, because it has 2 ends to it. Therefore, 5 times 2 gives us 10 as the sum of the orders. They just wanted 10, they didn't care about anything else. So, give them more detail than I need. Part B says, if Ollie's graph is also Eulerian, what numerical values can the vertex orders take? I got really carried away when I was doing this one and wrote down all the possible combinations of vertex orders that you could have. There are 7 of them, I think. They didn't want that. They just wanted you to write 2 and 4. They are the numerical values that the vertex orders can take. They have to be either 2 or 4. It's a simply connected graph. It has exactly 6 vertices. It's Eulerian. That means all the orders must be even. None of them can have order 6, because if they're order 6, that would be not simple, because you need to have a loop. We've already established that. None of them can have order 0, because if it has order 0, it's not connected. So the only values that they can take are 2 and 4, because they have to be an even number. So it was only 1 mark, so they wanted you to write 2 and 4, rather than the extensive answer that I gave. Part 4. We move on from Ollie. It was nice having him involved, but now he's gone. Polly appears. Now, Polly has drawn a simply connected Eulerian graph with exactly 6 vertices and exactly 10 arcs. What can you deduce about the vertex orders in Polly's graph? So again, it is simply connected. There are 6 vertices and 10 arcs. Well, hang on, we know some details about this then. If there are 10 arcs, the sum of all the orders must be 20, because the sum of all the orders is twice the number of arcs. Sorry, 10 arcs. So order sum is 20. Okay? So the sum of all the orders must be 20. Therefore, if the sum of all the orders must be 20, and they have to be 2 or 4, we've already established that, there's only one way you can do that. They must be, the only way to get 20 from 6 numbers that are only 2s and 4s is if 2 of them are 2s and 4 of them are 4s. That gives us 16 plus the 4 is 20. It must be 4 arcs, 4 vertices of order 4 and 2 of order 2. Finally, draw a graph that fits the description of Polly's graph. And they gave you some space to do this. This is 6. So I drew 6 vertices, and all that we need to do now is to try and connect these up in such a way that 2 of the vertices have order 2 and the others have order 4. So I'm not going to look at my answer, I'm just going to do it. Would it be alright? Yeah, I know. I don't know what I'm doing. I'm just drawing stuff. Hang on.
You're getting there.
Am I getting there? Where have we got to? So those are order 2. Let's go with 1, 2, 3. Does that?
Yes.
Is that all right?
The other one.
Yeah.
Join it together.
Oh yeah. There we are.
Perfect.
That's nice. Yeah. That's not the answer that I'm getting on here. I do a slightly different one.
Show us.
No.
Show the camera.
Yeah, I'm changing the camera.
Have to
Now
zoom
we have to go
in.
onto YouTube to find
And zoom in. It's just as good an answer. It's just a rearrangement of that, isn't it? Right, and that's it. That was quite a hard graphs question, I thought.